Hi guys. Okay, so let's look at this very important concept in thermochemistry and thermodynamics, and that is of enthalpy change. So in this video, we're going to be looking at the energy diagrams, and we're going to look at the calculations of the energy that relates to the reactions. Okay, so first of all, what is enthalpy? Enthalpy is a term that is derived from the first law of thermodynamics. And the first law of thermodynamics is that the change in the energy is the sum total of heat and work. And what is work? Work is equal to P delta V. Okay, so P delta V. So really, the delta E, that is a change in the energy, is equal to the sum of the heat plus the work done on the system or by the system. Okay, now we are only interested in the Q, which is the heat, and that is enthalpy. So what is E now? E is the internal energy, which is the energy that is present inside the system, within the molecules, the bond energy, and so forth. Okay, so E is now the internal energy, P is the pressure, and V is the volume. Now, in case we are dealing with systems which are gaseous, in those cases, if we keep the pressure and the volume constant, or in other words, there is no change in pressure, no change in volume, in that case, the enthalpy is really the flow of the heat, whether it is going inside the system or is it going out of the system. So that's one thing regarding the gases. So it's QP. But if you're dealing with the systems in which there is a reaction, chemical reaction, so we are looking at the difference in the energy of the products, and we're looking at the energy of the reactants. And that difference is called the change in enthalpy. And change in enthalpy is really the heat of a reaction. How much of the heat is absorbed or how much of the heat is released in a chemical reaction. Okay, so there are two types of reactions when it comes to the heat. One is the exothermic reaction, and the other is the endothermic reaction. Now, let's look at the exothermic reaction. Exothermic reactions, the heat is released. Now, here's one example. You have hydrogen as a gas, which is reacting with chlorine, Cl2 as a gas, okay? And this gives you 2 moles of HCl, and heat is a part of the product. So here, 185 kilojoules of heat has been released, and this heat is a product. Another way of writing the same reaction is H2 as a gas plus Cl2 as a gas gives you 2 moles of HCl. And there's a gap here or a space, and here you're going to write delta H, which is the change in the energy of this reaction or the heat of this reaction, or delta H of a reaction, and that is negative 185 kilojoules. Now keep this in mind. All exothermic reactions will have a negative value for the heat, exothermic. Now where does that come from? So here is one example. I'm going to show you here. You have, in this case, H2 and Cl2. These are the products, sorry, the reactants, okay? These guys, and I'm not writing there in the gaseous state because of the space reasons, but they already are in a very high energy state, as you can see from this energy and the reaction progress graph. So in this diagram, this is called the energy diagram, the products are at a lower state, energy level, and the reactants are already in a very high energy state. Every reaction, you will have to give little bit of energy to start the reaction, basically. Now, what happens is when these reactants are already in a very high energy state, means that they are already in a vibration. All molecules are going to be vibrating. So gently, they are vibrating. There's a little bit rotation happening. So they are like still sticking to each other. The bond is still maintained. But the moment you provide a little bit more energy, the bond begins to break. So the bonds of the reactants are going to break and the bonds of the products are going to form. So that is that energy that is absorbed in bringing about that change is called the energy of activation, and we represent it as EA. Okay, so here in this topmost part, we have the bond breaking happening, between hydrogen and hydrogen and chlorine and chlorine. So these two bonds are breaking and a new bond is being formed, which is between hydrogen and chlorine. So basically they switch places. So when we see the old bonds break and the new bonds form, so that state, in this state, this is called the transition state. Transition state. Okay, transition state. And this transition state is also represented as TS. Okay, now here's something important. These are, as we said, this energy, this is the HP, that is a product. So this is, as you can see, a small number, right? And here, these are the reactants. So I'm going to just put this as product, P, and here's the reactant, H. And as you can see, this is the heat of the reactants, which it has a bigger number. So what is delta H? Delta H is the heat of reaction, which is here, this difference between the reactants and the products. So HP, the heat of a reaction or the change in the reaction is going to be HP, the heat of the products, minus the heat of the reactants. So because of the space I don't have, but HP is the energy of the products, the heat of the products, and HR is the energy of the reactants. So HP, as you can see, is a smaller number. HP is a smaller number. Value of that number is small. And HR is a bigger number. So mathematically, when a small number minus a bigger number or a larger number, what happens? Your sign is going to be that of a negative. So therefore, the value of delta H comes out to be negative. Okay, so it would be a negative number. Now, another thing is the bond strength, the strength of the bonds. So here we see that the reactants, now that is the bond strength. The reactants are in a very high energy state. So the strength of their bonds is not that strong. It's weak, okay? So the bond strength of the reactants is lower than the bond strength of the products. So products have a lower bond strength. The products, the strength of their bond is, the products have a higher bond strength. Sorry, I take that back. So the products have a higher bond strength, but lower in energy. So they're more stable. The reactants, on the other hand, are already in a very high energy state. They are placed up. So their strength of the bond is weak. So a little bit of energy that you give and boom, it just gives away the energy, the excess energy, okay? And where does this excess energy go? It goes to the surrounding. So here you have the surroundings. It is given to the surroundings, and this is your system. This is your system right here. Okay, so the system gives away excess energy to the surroundings, and the products have a lower energy state, so they are more stable, and so they survive in a way, you can say that. Okay, so this is one. This is how you make sense of this negative value that comes through the in the exothermic reactions. Now let's look at the calculations. Now, for example, you are given, okay, let's see what is given to us, sorry. Okay, you are given a reaction, nitrogen, N2 as a gas. All right, N2 as a gas is reacting with 1 mole of nitrogen gas is reacting with 3 moles of hydrogen gas. Okay, and this is giving you 2 moles of ammonia. Okay, NH3 ammonia as a gas. And the heat that is also released is 92.2 kilojoules. Remember, we can rewrite this whole equation as N2 as a gas plus 3 moles of hydrogen as a gas. Now, sometimes on the exams, they are not going to give you a balanced equation. So you always have to check the balanced equation. So here you have 2 moles of ammonia that is being released or formed as a gas. And delta H is equal to negative 92 0.2 kilojoules. So either way, this is the way you write the exothermic reactions. Okay, so now the question here is, how much of the heat in kilojoules is released when nitrogen and hydrogen react to form 50 grams of ammonia? So you are given this, that you are obtaining 50 grams of ammonia. What is the value of delta H? Okay, so let's do that. How we are going to first remember that for ammonia. So now we are only interested in ammonia, and we are only interested in the amount of heat. Okay, so here ammonia is given to you in grams, and so first convert the grams of ammonia to moles of ammonia. Okay, so one more time. So here grams of ammonia convert to the moles of ammonia first of all. Okay, next is, that is the NH3 and NH3. Next, you're going to bring in the mole to mole ratio. Now here, in this case, it's mole to heat ratio, because heat is actually a product, but really it's the how many moles are producing how much of the heat. So let's do this. And then here, this is going to, you have to go through the molar mass of ammonia. Okay, and this is here, this piece, you're going to look at the balanced equation. Balanced equation. Okay, and then that's going to give you the amount of heat. So this is going to be our map. Now let's do this first. For the molar mass of ammonia, nitrogen is equal to 1 nitrogen times 14, 3 hydrogens times 1 each, and that gives you 14 plus 3 is equal to 17 grams per mole. Okay, so now let's do this. 50 grams, 50.0 grams NH3 ammonia times 1 mole of ammonia over 17 grams of ammonia, 17 grams of NH3. Okay, so the first step will convert grams to moles, but let's continue here further. Now, from the equation, you're going to see that 2 moles of ammonia are producing, 2 moles of ammonia are producing 92.2 kilojoules of heat. Okay, so this piece right here is this piece right here is converting grams to moles. So this gives you the moles of ammonia and moles of ammonia coming from the grams. Okay, and then this piece is the mole to heat ratio coming from the balanced equation. Very important to you make sure that the equation is balanced. Okay, and so what do you get the answer here? The answer comes out to be, 135 kilojoules. Okay, now pay attention. We have here negative. Negative means that it is an exothermic reaction. So this is already an exothermic reaction. So in your answer, even though there is no negative, sign, but you will have to bring this negative sign because this is an exothermic reaction. Okay, so for exothermic reactions, you have to pay attention whether the reaction is exothermic or endothermic. So for exothermic reactions, the value of delta H is negative 100, in this case, 135 kilojoules. So 50 grams of ammonia is going to release 135 kilojoules. So heat is liberated. Okay, how much of the heat is liberated? Is 135. Okay, kilojoules. All right, so this is the exothermic reaction. Now let's look at an example of an endothermic reaction. In the endothermic reaction, the substances, they absorb heat, which means that, for example, let's look at this example. Here we have nitrogen as a gas, and this nitrogen is reacting with oxygen as a gas. Okay, and here you will have to give some amount of heat to this reaction. So here in this case, it's 100 kilojoules per heat, or 100 kilojoules of heat. is being absorbed, and this is giving you 2 moles of nitric oxide as a gas. Okay, now another way of writing this reaction is N2 as a gas reacting with O2 as a gas. All right, and this gives you 2 moles of nitric oxide as a gas, and the value of delta H in this case is going to be positive 180 kilojoules. So just pay attention to the 2 ways of writing this, okay? And then let me write this nicely. Okay, so this is now the 2 ways of writing the same reactions. Same as the case here. Let me just put it properly. Yeah, it's done. Okay, so now we are going to see that the reactants are in a very low energy state. Nitrogen and oxygen, very low energy state. That is why you had to provide them so much energy to initiate the reaction. In other words, first the nitrogen-nitrogen triple bond, that is going to break up. Then the oxygen-oxygen double bond breaks up. And then you're going to see the formation of nitrogen oxide, and that's also 2 moles of those. Okay, so in this case, again, in the transition state, this bond breaks, and the new bond forms. So that state is the highest state. Once the new bonds are formed, then you are going to see that they come and, they settle down. But they remain in a higher energy state. Why? Because all that excess energy that was provided now has to go somewhere. So it gets absorbed by the molecules and it stays in their bonds. Okay, so you are going to study about bond energy also, but for now, just try to understand that energy of activation is the energy that is needed to start the reaction, break the old bonds and make the new bonds. So in the endothermic reaction, a lot of energy has to be given to them. In other words, you have to continuously provide the energy to the reaction till you get the desired product. So consider this like this. You are baking a cake or you're making a food in the kitchen, right? There is a certain time and a certain amount of heat that is needed to cook the food that you desire. You can leave the food cooking for as long as you want or as long as you don't care. You are not going to get the product that you desire, right? So in order to get the desired product, a very definite amount of energy in a very definite amount of time period has to be supplied to a reaction. So this is the energy of activation. In the case of endothermic reactions is very large. And what is delta H? Delta H is same. Delta H is equal to the energy of the product minus the energy of the reactants. So as you have seen it, that the reactants are in a lower energy state. Products are at a higher energy state. So in other words, products have a bigger number. Reactants have a smaller number. So whenever a bigger number, sorry, let me write this down with this one. So whenever a bigger number or a larger number minus a smaller number, okay, a smaller number, bigger number minus a smaller number, and that is the energy of the change in the reaction, change in the energy of the reaction. Okay, so that is why it is going to be a positive number. So delta H is a positive number because of that. Positive. All right, now comes the bond strength. So as you can see that the energy, the bond strength, BS, bond strength, or the strength of the bonds, bond strength. The strength of the bonds of the reactants is more than the strength of the bonds of the products. Okay, now you can see that the bonds are already strong, very strong in the case of the reactant. So you can see triple bond is strong bond, double bond is a very strong bond, triple and double bond is strong bond. In order to break them, you have to provide a lot of energy in order to break these 2 bonds. Okay, so when you do that, then the, the excess energy that you have already given to break this bond, it's all, interconversion of mass and energy, and the energy is never created, energy cannot be destroyed, but energy is transformed from one form another. So the energy gets stored in the molecules of NO, but because it's all that excess energy, large energy, that's why they remain like unstable. So lower energy, stable, higher energy, not stable. So let me just write this here. Lower energy in the bonds, or you can say lower bond energy, okay, equates to stability. Stability, okay, and vice versa. If it's a higher bond energy, less stable, okay. So this is one thing. Now let's do a calculation. For example, you are given a situation where this is the reaction. So you have 2 moles of water, okay, 2 moles of water, and this is in the liquid state. This is decomposing to give you 2 moles of hydrogen, okay, 2 moles of hydrogen as a gas, and 2 more, and then 1 mole of oxygen. Sorry, my hair. Okay, so 2 moles of oxygen as a gas. Okay, this is a reaction. I'm sorry, I'm going to just say this again. 2 moles of water are decomposing to give you 2 moles of hydrogen and 1 mole of oxygen, and all in the gaseous state, oxygens and hydrogens, and water obviously is a liquid. But here the delta H value for this reaction is positive 572 kilojoules. All right. Another way of writing the same reaction is 2 moles of hydrogen, 2 moles of water, sorry, they are reacting with, or they need 572 kilojoules of heat to break up into 2 moles of hydrogen as a gas plus 1 mole of oxygen as a gas. All right, now comes the question here. First of all, let's write down the conversion factors. So conversion factors. Here are your conversion factors, or that mole to heat factors. So that is 2 moles of water need 572 kilojoules of heat. Okay, another conversion factor is 572 kilojoules of heat over 2 moles of water, and this water is in a liquid state. Okay, 2 moles of water in a liquid state. So this is one, like 2 conversion factors of, like, when you compare water and the heat. The next conversion factor is with regards to the heat now. So 2 moles of hydrogen as a gas is released when 572 kilojoules of heat is involved in breaking the H2O, or in decomposing the 2 moles of H2O. So this is one, or 572 kilojoules of heat gives 2 moles of water, 2 moles of hydrogen, sorry, in a decomposition reaction of water. Okay, another is 500, let's do 1 mole of oxygen, 1 mole of oxygen, 1 mole of oxygen over 572 kilojoules of heat. So that's a relationship between them. And 572 kilojoules of heat over 1 mole of oxygen. Okay, and again, this is gas as a gas. It's very specific, the states are very important. Okay, so these are the different conversion factors, okay, between the heat and the reactants and the products. So now let's look at this problem here. You are given 9 grams of water, 9.00 grams of water. This is given to you. Okay, and you are being asked how much of the heat is going to be released from when you decompose 9 grams of water, and you want the heat in kilojoules. Okay, so this is given to you. So again, the first thing we are going to do is convert the 9 grams of water to moles of water by multiplying by 1 mole of water, 1 mole of water over the molar mass of water, which is 18.02 grams of water. Okay, so first is the grams to mole conversion using the molar mass of water times, now we're going to just move here, times, now we want the heat and we are looking at the relationship of water. So we want the heat and we want to find the heat and we are looking at the specific relationship of water. So why did I choose this one? Because it allows me to cancel out the moles of water. And the heat is what I want. I want the amount of heat. And this one is the moles of water I want to cancel out. Okay, so this is the reason why we use this conversion factor. So now just write down here positive 572 kilojoules of heat over 2 moles of water. 2 moles of water. Okay, so now what do you have here? You have the grams of water and grams of water cancel out. All right, moles of water and moles of water cancel out. And what are you left with now? You are left with 9.00 times 1 times 572 divided by 18.02 times 2, and this gives you positive 143 kilojoules. Okay, positive 143 kilojoules. Why is it positive? Because the heat is being absorbed. Here, the heat is being absorbed. You can see that this is a part of the reactant. So here delta H value is positive because we are looking at the endothermic reactions in which the heat is absorbed. So here you are going to write down that the energy is absorbed and the heat is absorbed. Therefore, the value of delta H is equal to positive 143 kilojoules. So it's very important that you look at the details in the question, whether so in the multiple choice, that's where sometimes we give you negative 143, sometimes we'll give you positive 143, and sometimes we go to none of the above. So it's very important you understand what the meaning of positive and negative. So negative exo and positive endo, always, no matter what the reaction is. Okay, so I hope that this was easy, and thank you so much for watching. Bye-bye.